Cut down on certain behavior.
Maybe site on the other side. It's not very much space, but it's still probably.
And I was like, oh yeah, you are.
I don't know. Never tried that. Never tried that.
Right. Already failing at that.
Yeah.
Okay, I'll keep that for the moment, but thank you.
I didn't go to the 9 a.m., so I'm fine.
Yeah, I know. I like that too.
That was good. Was it just like transportation?
Thank you. I got next.
You got next too.
Yes.
Oh, so I like what my husband was like. Yeah, I saw him this week. Kanye was hot.
I will petition.
Do you see the Do you see the regret? I'm always spreading out, you know that?
No, it's good to see you. I'm so bad at jumping my
No way. Are you guys good? I wish you were there. Oh, that's great.
I'm a little well, I'm
Screaming. Like this.
But then, like,
sorry.
You can't say it in German.
you're not gonna find this guy.
You go like the first dinner?
No, that was the second.
When's the last time I saw you? It feels recent. It's not even cold.
You're staying in your.
Until Friday is fine.
Right, you gotta
Putting
set
it on.
right.
Yeah.
I see.
Like, I really sleep and then I dropped the last one. So,
Yeah, I think we should
I can't decide. I really can't decide.
open all the windows and then
The problem with like I can
imagine starting at 9. Nice way to chat. I've had enough.
We're just crashing out. Just don't mind us. Yeah. You know, just
This is actually extremely very quick. He just happens that this is like
Well, I just have like finger you will be fine.
But the idea is
I know, I got it.
I just want to ask me, what do you do?
Okay. Hello, everyone. Right. Let's make a start. I don't have a new sign-up sheet for this week. I wasn't able to find Simon earlier, so I'm going to pass around last week's. If you could sign down the other side, you're going to have to make your signature slightly smaller. But if you could pass that round, I'd be grateful for that. Okay. There were a couple of mini lectures to watch before coming today. Does anybody want to ask any questions about those as a starting point? We can do that later if you weren't expecting that, weren't ready for that. We can do feel free to ask questions about those and what and today's lectures as well when there'll be time later on. But as that starting point, are there any questions? Are there any things that you find confusing or issues you want to raise from the mini lectures? Okay. And as I say, do feel free to raise any that crop up. So let's do a little bit of a hand show for this question, which is the question is, what is the real world value of climate sensitivity? So how much would the surface temperature of the Earth increase if atmospheric carbon dioxide doubled and held at that new level? So I've got 10 sections here, so just like to do a show of hands for each of these. If you think it's between 0 and 1, put up your hand. Between 1 and 2. Between 2 and 3. Hands higher. I've got to see you. Okay. 3 and 4. 4 and 5. 5 and 6. Higher than 6. Okay, that's cool. That was a bit tentative. It's interesting how this sort of question seems to get the same sort of result, whether or not you've been exposed to discussions of climate sensitivity before at all. So in the mini lectures, of course, there was a discussion of climate sensitivity. So you have that sort of distribution. How do people respond to that sort of information? And it was interesting that you maybe weren't looking around the room, but basically nobody was in the 0 to 2 degrees, which is kind of interesting because there is probability there below below 2 degrees. Quite a lot in 2 to 3, even more on 3 to 4, and then some on 4 to 5. It's it's kind of interesting how that sort of response to what you might have seen in lectures, what you might have read about, actually comes out in the distribution, because there's no reason that should be the case. You could have all looked at those distributions, absorbed that information, and thought, well, actually, the most likely thing, I don't know, is going to be at around 3 degrees, and we all go for that. But that's not what people do, and that does reflect the sort of uncertainty in the physical science system. So I wanted to talk a little bit about climate sensitivity as a starting point, because it's kind of important in terms of our understanding of the whole world response to increasing greenhouse gases. So a lot of what I'm interested in, and a lot of what I'm trying to get you to do in playing with the data sets last week, and was playing with the same and some more data sets this week, is to get an idea of the regional responses, because it's regional responses, it's local responses that have impacts on people. And yet the regional responses and the local responses are governed to some extent by how much the world warms as a whole. There is a global issue there. And you had this last week in terms of the energy balance issues. There's energy coming into the system, it's warming up the system. That's a whole world system. And so our understanding of that whole world problem is kind of important. So climate sensitivity is one route that we use to grasp that question of the whole world problem, the energy balance problem, how much will the world as a whole warm up, and that of course has impacts on regional changes. So here we have a figure from the IPCC Sixth Assessment Report 2021, Working Group 1, and this is from the technical summary. These are all encoded in these letters down here. You'll probably be getting familiar with Working Group 1 Technical Summary, IPCC AR6 2021. And this shows, I don't know whether I can shine a light with this. Not really. Okay. This shows the estimates of climate sensitivity and how they have changed over the last 45 years or so. Starting back in 1980 with the Charney report, which gave a range of 1.5 to 4.5 degrees. The first assessment report essentially gave the same range, although Charney had a best guess of 3. It was moved down to 2.5 in the first assessment report. Nothing changed in the second assessment report. In the third assessment report, nothing changed in the range, but they knew even less, so they weren't willing to give a best estimate, so it's sort of gone down. And the fourth assessment report in 2007, the best estimate went back up again to 3 degrees, and the range reduced very slightly to, I think that's 2 degrees to 4.5 degrees. And then the fifth assessment report, the range got bigger still. So they're saying, well, we kind of know even less. They gave a likely range, a 66% range of 1.5 to 4.5 degrees. They didn't give a 90% probability. None of these had probabilities associated with them. But in AR5 they said, well, actually, we think there's a up to 10% probability it could be above 6 degrees, and up to 5% probability that it could be below 1. But we really don't quite know what we are talking about too much there. And this has been seen for increasingly through this period as a failure of climate science, a failure to reduce this this uncertainty, this key factor. So, yeah.
Are these estimates based on the assumption that equilibrium would just stop after a certain point, or because if equilibrium continues, then the equilibrium just constantly increase, no?
So the point about climate sensitivity is it's the equilibrium warming in response to a doubling of carbon dioxide. So it's a fixed amount. So you can get there in different ways. In the climate model, you can just double it overnight. So in one day in the climate model, it's 280 parts per million. Next day, it's 560 parts per million. Full stop. Or you can get there in the climate model by steadily ramping up. They do scenarios called 1% increase scenarios, so you've got to doubling that way, or you can do it in more complex ways. But it's always at some aspect of a fixed doubling. A fixed doubling, I'm not going to go into this, but a fixed doubling usually taken to be from pre-industrial levels, so 280 parts per million. Although one of the interesting opinions about the way greenhouse gases interact with radiation is that that's not expected to vary. In principle, the direct impacts are not expected to change a lot if you double, say, from 400 to 800. And it will be the same thing. A doubling should lead to the same sort of thing, sort of, when you get rid of all the non-linearities and stuff, which, of course, is actually what's there and what's important. So you can just talk about doubling, but it's useful to talk about it in terms of doubling with respect to pre-industrial levels. So this has been seen as something of failure, and there's a lot of discussion in climate change science about how this is a big thing that needs to be resolved. I'm not sure I quite believe that, actually. I think this might just be an intrinsic thing of our limited ability to understand the system because of its complexity, because of our limited data. It might just be that we have this sort of understanding and we're not really going to get a lot better than that anytime soon because the data isn't there to tell us that. And we have to live with that. Anyway, whether or not that's true, there are aspects of the sociology of climate science here which become important, that there is a driver on climate science to try and reduce it. So there's a whole load of people trying to reduce climate sensitivity. And then there are a few people, like me really, who have been involved and published on climate sensitivity and are now involved saying that, you know, actually it's probably much more uncertain than we've given credit for, and that these probabilities of it being higher than we have previously thought are maybe higher than we allowed for. So in the SIP assessment report, they did reduce it. They kept a best estimate of 3 degrees, but they gave a 66% probability. They said it was likely to be between 2.5 and 4 degrees. And they gave a 90% probability that it's between 2 and 5 degrees. It's worth just reflecting on that a little bit. This sort of 90% probability between 2 and 5 degrees. You will have seen in the mini lectures the probability distributions, all these different probability distributions for climate sensitivity, and they're all skewed distributions. They sort of have a lot of weight between 2 and 4 degrees, but they have very little below 1.5 degrees, whereas they have quite a lot above 4 or 5 degrees. It's very much skewed to those uncertainty at the higher levels, and there's good reasons for that, which I won't go into at the moment, but there's good reasons for that. So the point about this 90% range is you can take the remaining 10%, up to 10%. It's not equally distributed either side. It's very heavily weighted towards the upper one. So maybe sort of 8 or 9% probability is above 5 degrees. And think about that in terms of the risk management aspect. If you go to your doctor and get perhaps a diagnosis of you having some disease or some some problem, or not. If it's a matter of saying, well, actually, you're fine, we're confident about that, it is very unlikely that you've got this. If they said very unlikely, you wouldn't think that there was a 1 in 10 chance that you've got it. In fact, in medical systems, it is usually about 1 in 200. That would be considered something that a patient could understand. But here we're talking about, it's very unlikely to be above 5, being 8–9% chance that it's above 5. Now this is quite a dramatic thing, because if it's above 5, if we're going up there, then of course the impacts across the climate system and the impacts to our economies are going to be quite substantially larger. So where do they get these numbers? Well, AR6 was more specific in how they got some of these numbers. They talked about the evidence coming from process understanding, instrumental records, paleoclimates, and emerging constraints. So that came in this figure, which is also a new technical summary of AR6. And what they've done is they went out and they assessed a whole load of different studies based on different lines of evidence. And these were the 4 lines of evidence they had. So you've got an instrumental record. What that's saying is you've got observations of the climate system over the last 100, 150 years, very recent records. The longest time series of temperature observations in one place is the Central England temperature record, which goes back, I think, to the 1600s. But you start to get widespread observations from about 1900, some from a little bit earlier than that. So that's what's considered the instrumental record. And for the instrumental record, they would say, well, you're talking about, I can't read it quite straight, sort of up to about 3.5 degrees. Then you've got your paleoclimate data. So this is data on what happened, whatever, during the last ice ages. So more than 10,000 years ago, sort of 10,000 to 2 million years ago, with the period when you've got in and out of ice ages and interglacials. Further back, you've got the Eocene and different states of the climate system, and you've got some observations for those periods which come from different sources. It's not my particular specialisation, but within the Ice Age periods, you've got ice cores that will give you those temperature records. So you can build up some idea of from those. And they would give you some sort of range which is a bit higher than the instrumental record. Then you've got emerging constraints. Now, emerging constraints, I do think, is almost designed to mislead. This is essentially model results, and this is what our climate models show. Not directly, because we don't believe our models directly, so we use a combination of the instrumental record. You might use observations of the seasonal cycle in the real world and the seasonal cycle in our models, and you would use that to say, well, our models aren't quite right in some way, so you can weight our models in a certain way, which gives this sort of emerging constraint. That's why it's called an emergent constraint. It's from the models combined with the instrumental record, but it's essentially a model-based result. And that's sort of goes whatever it is, 1.5 up to 5 degrees. And then you've got process understanding. So process understanding says, okay, what are the processes that impact climate sensitivity? How does the climate warm? What are the feedback processes that occur? How would we expect land surfaces and ice sheets to change? How would that change the albedo? How would that change the energy balance of the system? And that gives a much wider range. That gives a sort of 90% range that goes from sort of 2 to 8 degrees. So you've got all these different assessments, and then they combine them into a combined assessment to get 2 to 5 degrees. I think the main point I want you to take away from this, and indeed today's lecture generally, last week was all about kind of what we know, what we can trust. It's those foundations of why we should be concerned about climate change. This week's is all about what we don't know and why you should be, to some extent, constructively sceptical about climate change science and climate change models. You can't just go to climate change science and say, this is what's happening, this is what's going to happen, now I'm interested in the economics. Because it's not as simple as that. Because the climate change science is still a research discipline, and there are all sorts of fundamental things we don't know. And it's not just we don't know the answer, we don't know how to do it. We're still trying to work out how to do it. And one of those might be trying to assess how to assess equilibrium climate sensitivity. So, my own perspective on this is that climate change is an extrapolatory problem. We're driving the system into a state that has never been before, so the processes that are informed, the air-sea interactions, the land-surface processes, are going to interact differently in the future. Which means that your observational record is not going to contain the information about quite how they're going to behave in the future. This is a crucial thing when we think about economic damages. So do give Simon a hard time on that when you get to talk about that. But I'm not going to talk about economic damages now. But it's true even here. This instrumental record here is for the state of the system in the last 150 years. We're driving it into a new state where things will change. Ocean circulations will change. Maybe the Amazon rainforest will die back. The processes of feedbacks will be different. So you don't expect that to be encapsulated in the instrumental record. You could say something similar about the paleoclimate record. It's observations of the climate system in a fundamentally different state to the one we're driving it into. And then the emerging constraints, well, this is a matter of taking the models. Well, the models are not random samples of reality. The models are not even random samples of models. There's all sorts of this, which we'll come across later today. So in many ways, quite how you would get information from these three are, for me, extremely dubious. And for me, the process understanding is what gets us what we really know about how climate sensitive they are. And unfortunately, that's not an optimistic view, because that's saying your 90% level is up at the 8 degrees, with the 10% beyond that. And this, of course, matters. We've got this slide. This, of course, matters because it matters when we think about adapting and responding to climate change, but it also matters just in terms of global temperature response. So this is a figure that I created. It's the response, global mean temperature response to a low emission scenario. So this would be RCP 2.6. So a scenario which will give you a 50-50 chance of maintaining the global climate to 2 degrees above pre-industrial level. So that central line, your sort of best estimate climate sensitivity, kind of gives you this central line here. That's your 3-degree climate sensitivity. Your 66% probability coming from this combined assessment, so that's the, I can't remember, always keep forgetting the numbers, the 2.5 to 4 degree range. When you put that in and then look at, it's coming back to your question of the timescales, this is translating that into timescales. When you look over the next century with that range, you're now looking at sort of what, I don't quite know what that is, but about 1.7 degrees to nearly 3 degrees. Let's say 2.7. So that's already, that's an uncertainty, that's already a big uncertainty. So if you're trying to make policy to 2 degrees, do remember, and it really frustrates me how much in the media this doesn't come across, it's sort of, we're on track to stay in, to keep in 2, I'll come to you in a moment, to keep below 2 degrees. This is never the case. It's always a matter of best option is we're on track to maintain a 50% probability of staying below 2 degrees. And the other, and again, this is a skewed distribution. If we don't, then we could actually still be quite a lot higher. So you might aim for 2 degrees, fulfill all your international commitments, achieve everything that you want to achieve in terms of what you think is necessary, and you might still, with 66% probability, sort of be in this range of 1.7 to 2.7. And so if you got unlucky, we could be quite a lot higher. Now, there was a question. Yeah.
Yes, I think you somewhat alluded to it, but what is the relationship between the climate sensitivity outputs and the RCPs and the SSPs that we talked about last week? Like, is this for every RCP, for every pathway, is there a different climate sensitivity?
No, climate sensitivity is something that is a sort of descriptor of the climate system, and it's just something we don't know. So, so let me see, yeah. So if, whereas the RCPs are scenarios of future greenhouse gas emissions or concentrations in the atmosphere. So if you take an RCP, and this is RCP 2.6, and the single value of climate sensitivity, if you say, let's imagine we knew that, let's imagine we knew it was 3, that's how the climate works, then you would get this, then you would follow this black line. You wouldn't actually, because it's one of those, oh, now I'm doing what I always hated in my lectures and saying, oh, but I've said something which isn't quite true. It's going to be a lot more wiggly around that. This is just sort of a central, there's always going to be wiggles around it, but forget about the wiggles for the moment. You're going to be following that black line. So your RCP and your climate sensitivity are, the climate sensitivity is physical science uncertainty. Your RCP is social science uncertainty in terms of how is the world going to behave. I do like to think about it that way, because I think it's very reasonable when you talk to people, whoever they are, the public, media, but I tend to think about it in terms of talking to central bankers, business. These people might have an opinion about whether we will achieve RCP 2.6. They will have an opinion about whether we achieve net zero in 2050. They will see the political landscape and they will have an opinion. And you all will have an opinion, sort of, you know. We can make great statements, we can make statements, the Paris statements, these sort of things. But you will, each of you, have your own opinion about whether it's credible for global society to meet that. And I would argue that that's a perfectly reasonable thing for you to do. We'll all have your own opinions. On the other side of this, you've got climate sensitivity, which is a descriptor of the climate system. And for most people, maybe not everybody in this room, but most central bankers, it's not reasonable for them to have an opinion on that. They don't know what's going into that. They don't know where the uncertainties arise. It's not a matter that they can easily make a judgment on. So it's kind of important for the climate science to be able to put across the uncertainty as it reflects our best understanding that we have today. I mean, that went way beyond your question, but did that sort of address it? Okay. So your 66% probability based on the IPCC assessment would be 1.7 to 2.7. If you take a 90% probability, it's sort of 1.5 up to 3.5 degrees. So this is your 9 out of 10 chance that if you achieve an emission scenario that you have assigned to be good enough to keep you to 2 degrees, you might be at 3.5, just because of our understanding of the climate system, our best understanding today if you go to the IPCC. If you take me, which I haven't quite thought about it in these terms, rather says that I'm a bit of a pessimist, aren't I? I'm not really. If you take me, and I would say, well, actually, the process understanding is the crucial one here, and that climate sensitivity could be up to 8 degrees, then you're looking at something that goes from sort of 1.5 up to nearly 5 degrees, even under a scenario where you've achieved everything you thought you needed to keep it to 2. Yeah.
I have a question regarding the process understanding. How certain are we that there are no unknown unknowns? Like, could it be that in like the next years there emerges some mechanism that we weren't aware of that totally changed the mass of it?
So, I have a discussion of that in my book. By and large, I would say I don't care about unknown unknowns. So, because unknown unknowns are intrinsically unknown. It's sort of saying the world might be different to how we understand it. Yeah, the world might be different to how we understand it. Tough. We just got to live with what we understand. What really frustrates me and goes into this process understanding part is what I describe in my book as within that matrix, the unknown knowns. Yeah, okay. So your known knowns, this is all Gunspeldian uncertainty. Your known knowns, okay, stuff we know. Your known unknowns, you know there's stuff out there that we haven't quantified, that we haven't really understood, and you can build that into your assessment to some extent, particularly if you're a Bayesian statistician, you would sort of say, okay, I'm taking all this different information. I know that this is unknown, but I can play with that information. Where the problem comes is the unknown knowns. So this is, for me, different people describe this differently, but the way I describe it in my book is there is information out there. So these aren't unknown unknowns. People have thought about it. There might be statisticians who've looked at different ways of looking at the data sets. There might be modelers who have looked at different ways of modelling the system. There might be people who do biosphere research who have knowledge about soil carbon feedbacks that could change the whole scenario. Stuff that it's not unknown unknowns. Somebody knows it, but we have not been clever enough to draw that information together into a combined assessment. So we are conning ourselves into being more optimistic about what we know. Those really worry me, and they're everywhere. They are everywhere. I mean, they're going to be everywhere in society and they're everywhere in science, but it's particularly bad in climate change science because it involves so many different disciplines trying to interact, and we're not very good at getting them to interact. This is sort of my lobbying position and my research agenda, and indeed we held a two workshops in LSE 2 weeks ago, getting different disciplines together. It's quite exciting. The people are enthusiastic to try and make this better. Yeah.
Another question about the process understanding. Are these just individual processes that we know that exist added up, or are there also interactions between those?
There are always going to be interactions between
so
them.
Those are included in the estimates?
Not sometimes, but not terribly effectively. I'm going to come back to that because I can't quite remember what we're going to talk about. Yeah, I thought I was going to talk about that. Okay, good. So that will come up in a couple of moments. Okay. So what I'm trying to do mostly is give you a feel for how big the uncertainties are, where they come from, where you might want to go to find out more about them. This is beginning to be somewhat recognised. I just thought I'd show you this because this, for this group in particular, I don't know whether Simon will talk about this, but this is a report from the Institute and Faculty of Actuaries here in the UK, came out a couple of years ago, and called Climate Scorpion, with the stingers in the tail. And this is sort of meant to represent one of those climate sensitivity distributions, and it's reflecting concern amongst these actuaries that we are in the financial sector and in insurance and reinsurance tending to focus on this 90% range. In fact, not even that. We're tending to focus on the really central value, and we see that a lot in finance. So there's extra stuff from these workshops this other week. Some of those were with the Bank of England and with the European Central Bank, talking about the need to explore scenarios that start to explore these tails. Okay, so I think, I'm not quite sure why I put those earlier, which were sort of things that I've added recently, but it seems like it's important to introduce those. So to expand on those, talk a little bit more about these sources of uncertainty. So when we think about those process understanding, the uncertainty in I could get my pens and that. In climate sensitivity essentially comes about through uncertainty in the feedbacks. Did I get pens? Do I have pens? So, as was in the in linear lectures, let's see if I can write it down. It's sort of one of the really valuable equations, the energy balance equation. Was this. So this is an energy balance equation. It was in the earlier mini lectures. So you've got some forcing. This will be the radiative forcing, the extra energy going into the system, which if you increase CO2, you get this forcing, and that drives a change in temperature. That's the surface temperature, delta T. And there's a sort of an inertial factor, which is the heat capacity. And what that does is it leads to an increase in delta T, which increases the radiation going out to space. So it brings you back into balance a little bit. So the crucial thing controlling climate sensitivity is lambda, and that's because if you double CO2, you get some forcing related to doubling CO2, and ultimately it'll come to equilibrium, and when it's in equilibrium, the surface temperature isn't changing anymore, so that goes to 0. So in that situation, you get delta T equals F2 times CO2 over lambda. And F2 times CO2 is reasonably well known, not perfectly known, but about 3.7 watts per square metre. So your uncertainty, and this will be climate sensitivity. Your uncertainty in climate sensitivity comes all from lambda. So the point here is that the physical manifestation of climate sensitivity and uncertainty in climate sensitivity comes from these different lambdas, different processes. So one contribution to lambda is what's known as the black body response, and that's just saying if you put energy into the system, it's going to warm up. As it warms up, it radiates more energy, and that's your response. That is a value of about 3.2. Then you've got the water vapor response. As you put more, as you warm up the atmosphere, it can hold more water vapor, and water vapor itself is a very strong greenhouse gas, stronger than carbon dioxide. So as you warm up the atmosphere, it holds more water vapor, so it accentuates the greenhouse effect, and that's encapsulated by a minus 1.6. So that reduces the total. Then you've got the lapse rate response. This is a change in the rate at which the temperature in the atmosphere falls as you move up through the atmosphere, which affects the greenhouse effect. This is somewhat unknown, but let's take a value of about 0.6. Then you've got the albedo response, changing ice sheets, changing glaciers, changing snow, changing surface processes, and the cloud response. And the point here is that there are different values you can take for each of these because there's a lot of uncertainty. And that means you can end up with a value of about 1.6 or about 0.6. So this is a sort of range of uncertainty there. And Lost my clicker. Yeah. So, this from the IPCC AR6 gives you some sort of idea of what these different contributions are. They tend to bring together the water vapour and lapse rate because they're kind of connected. Yeah, so you can see you've got warming due to the Planck feedback, the black body feedback. You've got a direct feedback there, and then you've got various responses which accentuate warming, in particular the water and lapse rate feedback, the sectional feedback, the clouds, of which the clouds is the most uncertain. So this is, you were asking about the interactions between these processes. Was it you? Somebody was saying. Yeah. You were asking about the interactions between these processes. So a lot of this uncertainty comes from clouds, which is something I find it quite interesting that as a consequence there's a lot of work going into how we can understand clouds better. And that's fair enough. I mean, I don't object to that. But there's also one or two really interesting papers that show that how clouds behave is fundamentally driven by the surface temperature underneath them, particularly in the oceans. So if you get change in ocean circulation patterns, you will get different cloud responses. Which means that to understand the cloud response, you've got to get the oceans right. And you do have all these interactions in the same way. Anyway, so where do we go from? Okay, yeah, so the point about this, all this so far is we've got lots of uncertainty in climate sensitivity. That's kind of crucial for what we will end up with under any particular emission scenario. The physical aspects of the system that drive that climate sensitivity and the uncertainty in the climate sensitivity are particularly focused on albedo, water vapour lapse rate, and clouds. And so understanding, if we're looking to try and constrain things, understanding these processes are important, notwithstanding the fact that actually it's a whole system behaviour. So all of this then has been about the response of the whole climate system, the global response, global mean temperature. What I want to now move on to is to talk a bit about uncertainties in a different perspective. So here I'm now going to be thinking more in terms of how we use our models and how we interpret our models to tell us about particularly regional changes, local changes, which I would argue are sort of where you get that direct interaction with society. Yeah.
Before we move on, do you mind re-explaining the term above lambda on the board?
What do you want?
I missed your explanation before, and I can't read it.
Oh, well, I mean, I'm not sure. Okay, so F would be radiative forcing. F is it's the extra energy being trapped in the lower atmosphere and upper ocean system as a result of increasing greenhouse gases in the atmosphere. That leads to more energy in the system, which leads to an increase in temperature, take it as the surface oceans. That doesn't happen instantaneously. There's a delay in that because it takes time for that heat to lead to a change in temperature, and that's encapsulated by heat capacity, how much heat you need to increase. For instance, how much heat do you need to increase water by 1 degree is 4,200 joules. The ocean is an awful lot of water. That gives you a lag there. Nevertheless, you do get a warming. So delta T is the warming of the planet. If that was all that was happening, then the planet would just warm and warm and warm. It's just going to increase warming. But what actually happens is that as the temperature increases, the surface of the planet is able to lose more energy out to space than it could originally. So this detracts from the radiative forcing. So you've got radiative forcing due to carbon dioxide and other greenhouse gases, but then you've also got an increased heat loss due to the increase in temperature. And how much heat loss do you get with an increase in temperature? Well, how much heat is lost per degree of increasing temperature? That's lambda. Lambda tells you how much extra energy is lost. And if it were just a matter of temperature, if it were a black body and you heated it up and it just started losing heat directly, then it would lose it quite quickly, and the lambda would be about 3.2, and since F for doubling CO2 is about 3.7, you get a climate sensitivity of about 1, very slightly over 1. Unfortunately, lambda is not just that. You've got all these other things that make it worse, that lead to an intensified greenhouse, and we'll come to in a moment, greenhouse effect through the water vapour, and leads to a reduction in albedo. So this is not free, and it is reduced. And the closer to 1 it gets, the higher climate sensitivity will be.
On the graph, are clouds generally positive feedback? I know certain types of clouds.
Sorry, I meant to.
Are clouds generally like positive feedback? I know certain type of clouds, like cirrus clouds, right? They trap heat and.
No, so this is no, they're not. So this big uncertainty for clouds, you can see, goes from negative to positive, though it's thought to be positive, but still it could be negative. So cloud feedback is massively uncertain, as in it could be an ameliorating factor. It could actually reduce global warming, or it could increase it. However, that's not really true. It's overwhelmingly thought that it will increase the overall warming, and that is because, exactly as you say, clouds in different levels of the atmosphere lead to different types of feedback processes. Now you're putting me on the spot. I think it goes something like this. High clouds, cirrus clouds, higher up, tend to be thin clouds, meaning there's not that much ice, there's not that much water vapour, but they are basically white. So they increase the albedo. So the increasing albedo of clouds leads to a cooling of the planet. So it's a counter to global warming. And increasing low clouds is dominated by an increasing, an intensification of the water vapour feedback, but also ice, particularly the icing clouds, far strengthening the greenhouse effect, and they have a very positive feedback. So the question is, how do these two things balance out? And this is something where we've got quite a lot more knowledge during my career. Over the last 20 years, I think, 20 years ago, I think it was much more, we just don't know which of these is going to dominate. I'm not a real expert in this particular thing, so I can't say, but my sense is that we are now much more confident that actually the accentuating feedback, the low clouds, dominates this response. But it is still a very significant uncertainty. I want to talk through sources of uncertainty in climate forecast, thinking about climate models, and I'm going to categorise them into external influence uncertainty, initial condition uncertainty, and model imperfections. So external influence uncertainty, I don't want to spend very long on. When we talk about a climate prediction, We don't know quite what's going to happen because we don't know what RCP scenario to choose. That's a little bit trite of us to say it that way. We don't know how humans are going to respond. There's a human aspect here. What do we do is clearly a really important factor, and it is an important factor. What I want to get across to you as mostly social scientists is that it's not the only important factor, that actually uncertainties in the physical science are just as big. But nevertheless, uncertainties in quite what we do are crucial, and they're things that we can actually affect. So it's kind of important. Initial condition uncertainty is about how the prediction is affected by imprecise knowledge of the current state of the system at the smallest scale. So I mentioned this last week, where I sort of said the different, I can't remember what I was talking about exactly, but I talked about different simulations where you ran a climate model. Oh, that's right, beginning of last week. You ran a climate model. If you change, you imagine this climate model has sort of tens of thousands of points all over the globe, and at each of them they have temperatures. If you change one of those points by a hundredth of a degree, you will get a different trajectory going forward. And it can be really quite substantially different. Yeah, okay, we'll talk about that a bit more in a moment. Then there's model uncertainty aspects. So starting off with model inadequacy, when we think about our Earth system models, very complex models run on supercomputers, we know they're inadequate in a certain number of ways. There are processes that we know to be important that are absent. Things like atmospheric and oceanic chemistry. There's bits in there, but there's lots that isn't. Most of the models that we want to simulate climate don't include a stratosphere, and yet things like those cloud feedbacks and stratospheric clouds are really important there. So they're just not in there. So we know that the models are inadequate in that sense. We know that the parameterized processes in these models are unlikely to capture small-scale feedback, because the parameterized processes like clouds, like convection, like soil moisture levels, these sorts of things, they're not meant to represent exactly what is going on. They're meant to represent some average over grid blocks that might be 100 kilometre on a side. So these are, you don't expect these parameterizations to capture small-scale feedbacks, and yet small-scale feedbacks can rise into changes in the whole response of the whole climate system. So we have those sorts of inadequacies. What's the last one? Yeah, inadequate simulation of some processes which should result from the fundamental processes included. Yeah, so this is the idea that things like, for instance, hurricanes. Hurricanes are important for moving heat and energy around the system. They're important on the global scale as well as the local scale. But they happen on the small scale. In global sense, they happen on the small scale. They arise from processes, sort of the dynamics of the atmosphere-ocean system, the circulation patterns, that are included in the model, but not at a resolution that can get hurricanes. So the processes are in there, and yet you know that the climate's response to changing greenhouse gases isn't capturing things like hurricanes and the diurnal cycle of tropical precipitation. When you look at that, this can be just wrong. So you know that things that there are problems with our models, and that's just a context. You've just got to remember that. So, I mean, it kind of goes back to, I think, your question of sort of are there unknown unknowns? Yeah. So maybe I was a little bit harsh on that, and perhaps a little bit pedantic. You might call these unknown unknowns, although I might argue that we know what's missing, so we ought to be able to think about them. But it does go into the realm of unknown unknowns. Then there's model uncertainty, where we say, okay, given our model, yeah.
But the main limitation, yeah, pragmatically, is more about computational power, or we don't know how to connect the different interactions of the different processes.
No, I think it's more fundamental than that. Okay. I think a lot of people would say it's about computational power, but we have no. I mean, this is what I was talking about 2 weeks ago, so this is my lobbying position. So we have no idea what resolution would be sufficient. we don't know how many processes need to be involved. Now, I'm not going to talk about this today, but in my book you've got the Hawking effect, and small errors can rapidly increase to big errors in climate predictions. So, for instance, is it important that we separate out pine trees and oak trees in a model? Is that difference going to be important? It's kind of a really important question that we haven't even asked. But that sort of difference could be globally significant. My sense is probably not. But asking that question is kind of important. There are processes that are just not in there, and we've got to decide when it matters.
So you think the reason that the model is not producing cyclones is because there's certain things that we haven't put in that we either don't know that we should put in, or we just haven't considered to put in.
So the problem with our models is both of these cases exist. For cyclones, the processes are in the model, but we don't have the resolution.
Yes.
So there's a whole group of people arguing that we should, and I'm now getting my talks mixed up because I'm talking a lot about this these days, but it's not meant to be here. There's a whole group of people. Go away and read this. So, this was an essay I wrote on these sort of things. There's a whole group of people out there saying we need to spend a lot of money on very big models. We should be spending billions on very high resolution models that would, and that would resolve the cyclone problem.
Specifically, the cyclone.
Well, they phrase it in terms of convection, but it's sort of, but it would actually, yes, it would also resolve the cyclones much better. Where I argue in this is that will not get us better climate change predictions, because that was only the third point of my. Did I say it? I can't remember. Because that's only this one. You've still got all these. There's still all sorts of processes that we just don't understand, that we know are important and should be in there, and are not. And so we can say, well, we can buy more computing capacity and put them in there. We can only put them in there when we understand them. So circulation we kind of understand quite well, but there's other aspects of the chemistry stuff we're not. We're just not at that stage. So I have my lobbying position that actually we shouldn't be spending vast amounts of money going for resolution. And what my particular research work at the moment, myself at the moment, is say, okay, so what should we do? Let's say we did have billions. What would be how would we spend that to inform society to minimise risk? Model uncertainty is about those processes that are included in the models, but we don't know whether we included them well. So different parameter values, different parameterization schemes, different resolutions, trying to tease out these different things. What are the most useful parameter values and model versions to tell us about future climate? What is the range of possibilities? Now this is something we can do something about. So we have our multi-model ensemble. You saw that last week. We have multi-model ensembles. We have lots of different models. Lots. 30, 40 or so. We also have these things called perturbed physics ensembles, where you can say, well, we can go out and take our models and say, we don't know these parameter values, so let's try running it with different values and see what happens. How does that affect our conclusions? So we have ways of doing that. So one of the things I want to introduce to you, if you're not already, if you don't know about it, is these different ensembles. So firstly is this idea of ensembles. So it's lovely to think of the idea that you have a model you run the model, it's going to tell you what's going to happen. And there are sort of models like that in economics and in particularly specific physical systems, but that's not usually the case. What we're looking at in climate change models, complex climate change models, we're looking at a situation where we actually have a whole number of different models. They're all meant to be doing the same thing, and yet they get different results. So we run them all, and we look at all of them, and that would be called a multi-model ensembles. They simulate the same period with different models. So these are like one roll of several different dice. I've got a whole load of weirdo dice over there, but I don't think I've got time to show you those this afternoon. The alternative thing is say, well, there are initial condition ensembles. So that's how you take your model, but you start it off from very slightly different initial conditions, and it does something different. So that's like multiple rolls of the same dice. So it's saying if you have your dice, if you're trying to predict the outcome of a throw, that's going to be something you can only do in a probabilistic way. Because you run it, you throw it once, it comes up with a 6. But you throw it again, it might come up with a 2 or a 1. You can only came up with a 1, have you can only tell that by rolling it. You can only tell those probabilities by rolling the dice multiple times. An initial condition ensemble is the equivalent to that with the climate model, where we run the model lots of times to find out what happens. And multi-models would be saying, okay, we're going to take different models and do the same thing. It's like rolling different dice. So yeah, I don't have time to show you these, but this dice has an 8 on it. I've forgotten what number it doesn't have. A 3. I think it doesn't have a 3 and it has an 8. So the point is that it's something different. I have some others, you can play with them later. This one has a 7 on it. But it's kind of fun. As I say, I don't really have time to sort of. I've got some games, but I don't have time to do these again. I think this one has a 7 on it instead of. That's a 3. No, it's a 2 that's missing. Whatever. But this one's loaded. So whereas this one is a fair dice, it just happens to have an 8 instead of a 3. This one is a loaded dice. It does have a 7. It's actually a 7 instead of a 6, but it's heavily loaded towards a 4. This is the kind of thing we're talking about in climate models. They do different things, but to understand what any one of them do, you've got to roll it lots of times. Yeah.
Looking at the results from these models, is there something that would be equivalent to a notion of standard deviation to understand what's a big difference and what's a small difference? So if the temperature is 3, is 3.1 very close to 3, is 3.25 still close? At what point do we say, that's a big difference or a small difference? Maybe it's a question from a damage perspective, but from your perspective, from a physics perspective, is there that notion somewhere?
Not really, but can we park that? Because I do have a slide later that speaks to that a little bit. Okay. Yeah.
In this case, are the dice the different models or the same model with the variation allowed?
So they are different models, or they are models with changes to parameters, which is essentially making a different model. So same sort of thing.
Just changing the assumptions.
Yeah, changing the assumptions. Yeah. Crucially, though, you will see these different ensembles. These are available to you in the wider world, and climate information providers get access to these models. So you have initial condition ensembles and multi-model ensembles, but you need to be aware that they tell us different things. So initial condition ensemble tells us the probability of the outcome within that model. It's only that model, it's not telling us probability of reality. We need to escape from model land for that. But it's like that rolling the dice multiple times will tell you the probabilities associated with that dice, even if it's a loaded dice. It's, you can get those probabilities. So initial condition gives you probabilities, but only within that model. And the multi-models, if you run lots of different models, then you begin to explore the implications of errors in the way the model is formulated, and they give this idea of the possibility space of different outcomes. But they don't give us the probabilities of different outcomes, for all sorts of really interesting reasons, which I'm not going to. Okay, so that leads us to this question of how do we use our computer time? We have limited amounts of computer time. How do we use it to inform society, inform business, inform planning, inform science? What is the best combination? Should we be increasing resolution? Should we be increasing complexity? Should we be increasing the size of the ensembles? All of these are going to lead to a lot more computer time requirement, and so there's a balance there, and that's a difficult thing that we haven't yet been able to resolve, and is now, after about 15 years, leading to something of a well, I'm just creating trouble, really. There's people out there saying we need to run these high resolution models, and they haven't actually got the money for it, and then one or two people, of which rather unwelcomely I seem to have been dropped in as the person to argue this, that that's not the way to go, but arguing that we do need ways to go. We need to think carefully about how we get the information to support business, to support adaptation planning, but also to support narratives in society. Because I would argue, really going off on one today, I don't know, but must be feeling a bit more relaxed. If you're going to persuade electorates, if you're going to make a significant change in response to climate change, then you need electorates to buy into that. And I would argue that most electorates need to be presented with information which reflects how this is going to affect them in some way. Now, that's not the same as local predictions of temperature change and precip. I would argue that it's perhaps what you guys are more interested in. It's its consequences for society. How will society work? Economic consequences. But they themselves are driven by local temperature changes and precip changes and ability to grow crops. So you need that local information, I would argue, even for the mitigation side of this problem. How do we get that? What's the best way of getting better information?
I just had a question. I just thought this be something that AI could do.
So, no. So AI, and it is a problem for people think it can. So it's a real danger here. So you're working hard to make sure I don't get to the end of getting where I need to be. Okay, but it's a really good question. Okay, so AI. Why doesn't AI solve the problem? So AI, or more specifically machine learning, has a fantastic potential and is already beginning to achieve its potential in weather forecasting. And the reason it's good at weather forecasting is that the information, if you've got lots of satellite data, you've got lots of other sorts of data, you've got vast amounts of observational data, basically. So you've got a lot of training data, and it's training, it gives you it contains the information about how weather develops on short timescales. And as a consequence, machine learning could theoretically extract that information better than simulation models. And it's on the point of doing so. It's doing really well. I'll come back to that in a moment. Climate is an extrapolatory problem. The weather systems will change in response to changes in relatively slow components of the system. Ocean circulation patterns, soil moisture, land coverage, these sorts of changes, ice, these sorts of changes in the system. information about that sort of change isn't in the observational data set because it's changing too slowly and we have no observations of the future. So it is fundamentally a different problem, and the information we're looking for, you can say a priori, is not contained within the observations we have. So machine learning and AI not only can't solve this problem, but worse than that, it will tell you it can, because it can process that and give you an answer. But it's back to what we know and what we don't know. We know that that will be the wrong answer, and yet people are still doing it and still providing that information. So that's not to say that AI doesn't have a role within the climate modelling world. So within the mini lectures, that discussion of parameterizations and how you represent particular parts of the system, you can imagine using AI to train up something that encapsulates a particular process better than we have at the moment. So AI could be really useful in building better models, but not directly in solving the system. It's a battle we're fighting at the moment. Yeah.
So we can see these climate models more as like networks, right? Like more networks that are connected and are looped. It's not like a statistical problem, like in terms of regressions or something like that.
Yeah.
Here is more network, everything's connected.
Yeah, absolutely. Different disciplines phase these things differently, but yes, absolutely. That's a good way of looking at it. Okay, so way beyond what I was meant to do, so let's just say a few things. So we've got these models, these Earth system models, that's in the main lecture. You can run them, simulate the future, and you get sort of results like this from the IPCC back in 2007. What was nice about this was you've got one scenario. So these are different scenarios going down. So this is the B1 scenario, the A2 scenario. You don't need to know about these because these are too old, but they're a low emission scenario, high emission scenario at the end of the century, and you've got some pattern of response. What I really liked about this back in 2007 is next to these maps that you automatically go to, you have distributions from different assessments of quite what the global temperature change could be. So this, of course, just has one value of global temperature change. You've got to imagine that there's a whole range of those that are plausible, which gives you something of the uncertainty in what these might be. In AR5, same sort of thing. We've got with different RCPs. Same sort of thing with AR6, where they focused on same sort of thing, a best estimate, average across the. This is average across the different models, so it's a multi-model ensemble, but you take the average of it. That will be your best estimate. I don't really want to talk about these at the moment because I don't have time. And this will be the warming at the end of the century. Or you can cut across it differently and say, okay, let's look at what the pattern of response would be at 1.5 degrees warming, or at 2 degrees warming, or at 4 degrees warming, and AR6 did that too. And then you have the same sort of things with precipitation. There are less consistent responses here, where we have stippling. So the dots show the model response is large compared to the natural variability. So you see that by the end of the, what am I assuming? These are both different ICPs, aren't they? So these sorts of areas here, you do have a consistent response even in the precip. Where you've got hatching, it's, the model's response is small compared to the variability within the model. So you get large areas, basically the areas we care, a lot of the areas we care about. I mean, to be quite honest, the Antarctic circumpolar ocean isn't our #1 concern for adaptation at the moment, but various places on the continents are, and many of those places actually have less of a clear signal. Same sort of thing in AR6, where they map this onto different temperature changes. Okay, so yeah, this is what I wanted to do before breaking. I just wanted to highlight this point of, I guess I'm labouring a point, you probably all got it, but it's what I do, and I kind of idea. So talk about dice, and dice as a form of uncertainty. How does that map onto, and I've talked about models saying, okay, you change the temperature on a grid box and you'll get a completely different trajectory of response. So that feels kind of, well, maybe it doesn't feel weird. It doesn't really feel weird to me, but it seems to feel weird to quite a lot of people. Surely this is fairly predictable. And so what I wanted to highlight is just the field of nonlinear dynamical systems as being an important issue here. So you can take things that you understand and that are entirely predictable, and once you couple them together, you can get something where predictability is much, much harder. So, for instance, if you take a pendulum, so this is a clock we've got at home, it's called Fred. It's a pendulum, and so the point about pendulum is it's really predictable. You set a pendulum going, it swings very regularly in a predictable way, so predictable that it's been used to measure time for want to keep your link annotations? No idea I had any. Okay. So I'm hoping this will run. Will this open? Oh, okay. Hopefully this will work. Hopefully it won't make too much noise. Sometimes they make a bit of noise. I'd forgotten that the LSE computers do tend to be extremely slow. Okay. When you put one pendulum on top of another pendulum, its behaviour can be very, very different. And it becomes kind of unpredictable. And if we just go back to that. So the idea here was that if you start these are two pendulums, identical pendulums. If I start them off at as close as I can to the same conditions, and then set them going, they stay together for a while. Already they're starting to behave really quite differently. They head off and start to do vastly different things. And as you saw, they're not doing the same thing. And these are the same system. It just shows this idea of the difficulty in predicting a complex system. And the Earth system is a complex system. So, I'll remember next year to load it up earlier. So another example of that, which is, I'm not quite sure you necessarily need to know, but it comes from the Lorentz 63 system. It's the source of the term the butterfly effect. It was developed by Edgar Lorentz in 1963, or at least it was published in 1963. And you have a series of equations, they're differential equations, but they're fairly simple differential equations, but they interact with each other. And what they tell you is how X, Y, and Z change together. And then you have a map here of X, Y, and Z in three-dimensional space, because you've got X, Y, and Z. So what these equations do is they tell you that if you start here, you're going to move round here and do that sort of thing. And this is called an attractor. It's called a strange attractor because it never repeats. It never goes back to its original starting point. So that's one thing. Now imagine you had equations like this. You know what they are. That's the system. There's no model error here. But now take our starting conditions and change those starting conditions just a little bit. So you've got two places that start very close to each other. And you've seen where you can predict one with the other. And for a while you can. They stay very close together, and then boom, they can do something entirely different, go off in completely different directions. Those equations are actually the sort of equations that are used in climate models. In fact, those equations represent convection as a type of behaviour that is included in the climate. So we expect there to be this aspect of sudden changes, of unpredictability, which even if you have the models, even if there's no O in the model, and this has been demonstrated in a number of projects, but this comes from Clara Dessa's work back in 2012, where she ran, I can't remember, 50, no, maybe 47 simulations with a global climate model, and looked at, okay, let's see the range of behaviour of the change in global mean temperature in response to greenhouse gas forcing, and the change in the global response isn't very much. It doesn't vary very much. This is about climate sensitivity. The climate sensitivity in the model is almost a fixed thing. So the response of the model actually isn't susceptible to this chaotic variability because it's just empty balance. This is the sort of what you know. This was last week's stuff. There is stuff you can know. This is really quite well known. But if you go to subglobal scales, and this is already still pretty big, this is an average over the continental US, then you could get a change over 50 years of anywhere from under 1 degree to over 3 degrees from the same model. Same model, the only change is that little change in starting conditions. So the point is, so the point is that these uncertainties are absolutely a crucial part. They're inherent. You're never going to get rid of those. So I've taken way longer than that. I'm going to need to replan my second half a little bit. But at the beginning of the second half, I'm going to talk a little bit more about the model uncertainty. And I'll try and get rid of a few slides so that we can get on to looking at the data. But you're going to need 15 minutes to recover a bit. But yeah.
Just a quick question. So is the uncertainty still measurable, or is it by order of magnitude?
Is what, sorry?
Is the uncertainty by order of magnitude different, or is it still measurable? Because if it's not by order of magnitude, we can still, like, is it within a limit, we can still measure what's the cap of the.
I think if your difference is 1 degree or 3 degree average over the continental US, I'm not sure order of magnitude is the thing, because your issue is how does that affect your economy? And clearly 3 degrees is going to affect your economy massively differently to 1 degree, because you need to look at the ultimate thing. So it doesn't matter that this isn't an order of magnitude, it could well be an order of magnitude in response of American society. Okay, 15 minutes. Yeah, a little before 40.
I think over the curve, not that.
I don't know how to get out of it.
Sorry. No, you just
for the next session.
I've not seen it yet. So,
But like now it's kind of been like tampered with because it's cats.
They don't have it. No, they don't have it. Whenever I walk past, I keep me. They used to have it, and I know they don't have it now. And I keep.
That's so cool.
我只是看到它是那个
You can get it online.
Original
You can get
artifacts.
it online. Yes. Waterstones might have it.
Actually, so funny that you bring that up.
So at this workshop a couple of weeks ago,
And I was like, oh my god,
somebody did
P&A
say,
so
I've just bought your book.
I gotta go.
So, so somewhere around his must have it. Maybe. No, I'm a bit disappointed.
No, I'm
But that's very kind of you. But it is available.
I told them to order it.
Thank you. I will tell them.
About to go get China. Yeah, there's a lot. It's like strong. There's a lot. There's one in front of me, like right there. I think
It's still a win.
other bad ones.
Yeah.
Like, he was talking about, I was saying how I've been
Oh, very cool, yeah.
I'm a maniac. Have you guys met? I was just talking.
Or is it bought by the intent in the economics?
Because I early after, so I'm like, hey, once we get
But this is a battle I have.
going to the Natural History Museum.
I'd love to say challenge Simon on it. And you should. But I think Simon is probably fairly closely beaten me. But I don't know. There are lots of economists. There are lots of economists and social scientists who kind of see the physical science as being quite relevant. And I think they're just around it. I think they really are. And that sort of genealogy stuff. Well, I mean, the uncertainties in the models are huge in terms of those responses, which is kind of why I was doing it when I started. I never know quite the way I can get this across. It seems so dry. But if your climate sensitivity has a range of 2 to 5 degrees, or maybe could be 8. It's massive. If you think you can assess
The mailing list of this.
No, it's not just because they ignore it. Or I think they don't even know it's there. I mean, which I'm very critical of, but let's face it, the physical scientists have no real idea what it is. So they're not being so helpful. This is my field at the moment. I'm this battle if it's going to do good climate
It's going to have great time. No one really talks about
if you're going to do good climate change science, you need, if you're just doing science and you want to know about climate, fine. But if you're going to go around concerned about the planet, then I think it's useful. Then you have to economists and the social scientists, because what you think is useful is not useful at all. Just because my book came out a couple of years ago, it sort of led up to this workshop a couple of weeks ago.
You could score.
I've done my bit. I'll do my best. But really, this workshop. Very few other people feel thinking about it like I have, or they want to.
I had a good answer. Like, and then back up for the rest of the
really a big appetite. And lots of my climate scientists have basically never been in the room with they think I'm the economist. Probably should be. I'm not. So I'm now maybe a bit excited again. Maybe there's something to do. You're welcome. Hi. So you didn't get. I think it's been moved over there 5 minutes ago, actually. Somebody took it over there. So when people back in, I'll give it a call. Remind me if I don't. Sorry.
Like a check.
That's so
Yeah.
You should speak to the other brother.
No, it makes sense, and also like I get like the oil, like you don't want oil to come from the U.S. and stuff like that. Like I do get, I get the thought behind it about the pipeline and just obviously invested so much money.
Yeah, that was.
Yes. Yeah, because we have all the actual refining centers and then we'll send it back to you, but then no, it just sucks because crude oil has no, like it is so competitive that nowhere around the world crude oil is cheaper. But the refining and the like nature of it, like I just think it's really stupid that it's like the first, like I do get it because like I feel like it's a good idea for Canada.
Whereas like coffee,
but that's just such a frustrating thing when like there's like all this hoo-ha about the environment. And I feel like that's also just a staple of the head and then when people start trying to do
yeah, there is. So I tried that. Yeah, you should see. I did the black that's what I so I was like, no, that
I want to read it.
I really would.
You guys? I know, right? And then I also my own lunch. Like I bought in the ties that was really big for sandwich, so I ended up having to buy something extra. I was like, why am I not doing that?
I have to say, like, still,
You're like, I believe it. But I'm getting it shut in the foot like
it's gone off my screen.
yeah, you're like, look at me now.
Yeah,
It was really nice.
oh my god, this cheese is so
You're the only one that brings it. And I'm like, no, seriously. And then, yeah, we just so
I bring a broccoli.
yeah, nice. Yeah,
Like like rice back.
I think there were a couple of people but it was
Pretty brave. You don't want to be out there.
Oh, I was like,
You're so I'm just reading it. Guess what it's
yeah, right.
Yeah, so I spent a ton of time, but also typically my partner and I doesn't each other, so
Yeah.
I felt bad. I should have responded. Federico texted me. He was like, "Yes, balance out the numbers." I'm sorry.
Took a picture and he was like, this guy.
You know what? That's like being in this program. Man. Just gotta get used to it.
I feel like that we're like,
The other day I was like,
Magic touch.
well, like the inside.
No, it is kind of surprising. Well, I guess environment is kind of cleared or whatever.
It would be interesting to like I have a really like awful, like whoever the help. No, just saying it's funny. Yeah, no shit. Yeah, I'm like, hey guys. So me and Uncle Child, oh my
I mean, not with us. Not at all. Like they just want to stay in. I'm like, what are you doing? We're gonna row. Oh yes, that's good.
I'm not you have to make a balance.
I heard all these stories. Oh, and also my friend. He had like a very little bit. Can you tell me what's happening? He ended up having surgery on his liver. So I told him, I am the only person who can help. So we go to a restaurant. And we're like a collab. And we have I know, I was like, they're all carrying me on. That's what he did.
Monday we went to a bar and we had like live music. On Saturday morning we went to the beach. It was alone. We were young, definitely. We got to the tour like
oh, my bad.
The medical one.
Let's cover on a little bit. I'm not quite as far behind as I thought I was. Okay. I don't know. Okay. So I've okay. So, sticking with errors and things, like talking about what ensemble implementation. So, just the first point, this is no slide, but as I said before, sometimes the old ones are less, so I think this comes from but the point is that this is from a collection of different models that went into that report, at the time. And these are just the surface temperatures in those different models. And if you look at it like that, what you see is that you've got a load of different models, and they all look pretty similar. And you also have the top left one there is actually observations. And so they look pretty good. It's pretty good models. Yeah, you can sort of say that's pretty good. On the other hand, if you look at the, it's in the same report, now you look at the difference, the errors in the model, the difference between each of these individual models and those observations. So the observations stay the same, but now we're looking at the differences. So now, well, it depends on your model, but in different models you might have a 3-4 degrees, a region that is 3 or 4 degrees cooler than reality, or 3 or 4 degrees warmer than reality, or in some of them you might have the whole of the Arctic sort of Antarctic 5 degrees warmer. These are big differences. We'll say a bit more about that in a moment. Pretty much it. So if we jump forward in time, this is the CMIP6 ensemble that was heavily used in the 6th assessment report. And this plot shows the time series of global mean temperature from 1850 till the black line here is the observations. All the other lines are from the models of the CMIP6 ensemble. And what you can see is that many of these models are just completely inconsistent with those observations. You could be a degree warmer or a degree cooler. And what I have on the left-hand side is the same, pretty much the same plot. I think I filtered it slightly differently. But what you have at the top here is a probability distribution from one of these. One of these models has a large initial condition ensemble, so lots of runs with the same model. And that means you can build a distribution across this time period. So rather than a single simulation, you've got lots of simulations, and you can say what's the probability within that distribution of these different models. So you can see sort of something about the range of behaviour that you get within an individual model, which kind of tells you that it is completely different to observations. Now this is, I'll just show one more here. These are the CMIP6 global mean temperature. These are CMIP6 global mean temperature change, which is what you tend to see in most of these reports. We tend to be focused on that change because that's what we're interested in with respect to climate change. And when you look at the change, you've got to squint a little bit, but they can be quite good in the sense that they all show this warming towards the end of the 20th century. So they're all capturing that warming, and yet they're all very different to reality. And I have a different version of this, which I give in different talks, which shows regional absolute temperatures. So in central North America, you have a range of 6 or 7 degrees in the regional temperatures. And the point is that that exactly reflects this sort of issue. If you've got 6 or 7 degrees range, maybe you're 3 degrees different from reality in your between your model and observations in a region, that means the amount of snow you get there, the amount of rain you get, the soil moisture, the sort of land cover you will see, the snow line, all these things were going to be different. So the ecosystems are going to be different. Everything that's kind of important for this model is going to be different. And that means, and those are going to impact those feedbacks. They're going to influence the land surface change, they're going to influence the amount of moisture that's generated, which will influence the amount of clouds that go up above it. It means that the model is fundamentally different to reality. Now, this isn't meant to be a give up. This isn't meant to be a climate skeptic talk. It's meant to be that we need to be clever about using our models, and we need to not just be trusting them as telling us what's going to happen. And that argument about being clever, I'm going to just try and hammer home with the parable of three statisticians, which was put together by my friend and colleague Lenny Smith, who was at LSE but is now gone back to America. And he's American, larger than life sort of person, and if you ever get a chance to hear him talk, he gives a great talk. And he's proudly American, and he's proudly from Florida. And he's a dynamic system statistician. And he came up with this, the parable of three non-Floridian statisticians come to a river and they want to know if they can cross safely. Now, the crucial thing, as far as Lenny is concerned, is they're non-Floridian because they can't swim. His argument is that if you were brought up in Florida, you would be able to swim. But these statisticians can't swim, and they want to cross this river. And so, being good statisticians, they each make a forecast of the depth of the river. And so you've got three different forecasts. So what we now have is an ensemble of forecasts. And what they do is they average their forecasts. They take the ensemble mean, which is this line here. And under the ensemble mean, is this a good idea? No, this is not a good idea. This is not a good idea. Under the ensemble mean, they can cross safely. Under each of the three different ensemble members, they will drown. And the point here is simply that the ensembles contain lots of information, but we need to be really careful not to destroy it. And the question is how we combine that information, how you learn from these models about the actual decision that you're trying to make, whether that's an economic assessment, whether that's an adaptation planning decision, or some policy decision. And that might seem a little bit obscure and ephemeral, but all these plots I was showing earlier, these are all ensemble, multi-model ensemble means. All these things that are highlighted in the IPCC report, this is a multi-model ensemble mean. This is a multi-model ensemble mean. Okay, so moving on from that, within the mini lectures, we talked about different models and different the parameterizations within the models. In the perturbed physics ensemble, you take parameters that reflect part of the parameterization schemes and you change them. So these parameters might reflect how much ice there is in clouds, or how clouds interact with radiation, or how deep in the soil different types of plants can take up moisture. That's the sort of thing that these parameters tell us. We can take those. These are not well-constrained things. These are not things where somebody has gone out and measured them in reality. You can't go out and measure them in reality because they don't exist in reality. Because these are descriptions of something that takes place over a 50 kilometre by 50 kilometre grid box. So if you think about clouds, if you think about ice in clouds, there's a parameter in some of these models called the ice fall rate, and it's how quickly ice falls out of these clouds. 10 years ago, nobody had ever measured that. We now do sort of measure that, but it's still irrelevant because it's irrelevant to the model. The model is how ice falls out of a quantity which represents a percentage of a grid box covered in cloud, how much ice is going to be in that. This is controlled by the ice fall depth. So it's not something you can go out and measure. So you've just got to tune it. You've got to choose some value. And when I was working on these things 20 years ago, I took a value of 1 meter per second. There you are. Why? Well, it kind of worked. So you can change that. The point is that where you can't change basic physical constants, these are not basic physical constants. They're stuff that are used to describe something that isn't even quite reality. So we don't know what they are. We can change them. We can change those the value of that ice fall rate and see what the model does. And there have been a number of projects that do that. They're called perturbed physics ensembles. They're kind of dear to my heart because I did my early part of my academic career in this sort of thing, setting up this project called planprediction.net, where we took a model and we created these perturbed physics ensembles by taking these parameters, these collections of parameters, and changing them and seeing what the model did. Now, ideally, we were going to do that for different forcing scenarios. We didn't double CO2. We did do different initial conditions for each of them, so we have a combination of initial conditions and perturbed physics. So that brings us back to that availability of computing power. We were facing that same problem then, we're still facing it now. What we did with this project was I got the model working on the Windows on the PC so that we could distribute it. We could ask people to run it at home. And we did. We had over 300,000 people downloaded the model and ran it forward. So it got us that computing power, which would be no good for running a high resolution model because it's too distributed. But if we're running lots of parallel models, that was something we could do. We still needed to, this is not a perfect thing. It was 20 years ago. It's not a perfect model. It's not even, it has all sorts of flaws in the design, but it demonstrated the method. So what I wanted to highlight then is just to remind you what the different sorts of models we've got. We've got multi-model ensembles that you will find in your IPCC reports. CMIP2, CMIP3, CMIP5, there was no CMIP4. Maybe that's hidden away somewhere. No, this was to align it with the IPCC cycle. So CMIP5 went with the 5th assessment report. CMIP3 with the 4th assessment report, so they realigned it. But you typically have, and say this is a little bit out of date, sort of 30 to 40 models in these multi-model ensembles. And you might, for each of those models, have a simulation under one of the RCPs that might have up to 9 initial condition members. Bear in mind that that Cloudessa work that I showed earlier had sort of nearly 50 members to begin to explore that sort of range of behaviour. I'll come to this in a minute, but I will give you access to some of the planprediction.net results where we had close to 500 initial condition members so that you could explore initial condition uncertainty quite well. My point here is that one doesn't explore it at all. It's like one roll of a dice. Even 9 rolls of a dice doesn't really get you the probability of the outcomes of rolling a dice. 9 rolls of a climate model is not going to tell you what happens in London in that climate model. So it's limited, but it does have multiple models. Initial conditional ensembles try to go beyond that. So yeah, with planprediction on that we have 500 Cloudessa, 40. There are a few other projects. Increasingly, there are projects around now, in recent years, have done more of these. And then you have these perturbed physics ensembles, of which planprediction is by far the biggest, but there are a number of those around the world. So the other thing to say about this, as I've already said, is that the focus tends to be on regional responses. a lot of my interests, and I would imagine ultimately some of your interests will be, we want to know what's going to happen here. So that doesn't have to be the UK, it could be in Ethiopia, it could be in Maharashtra, or wherever you want it to be, but it's local information. That's what we're usually looking for. So, so the question is, how do we use these ensembles to guide local decisions? And how do we look at these ensembles? So I want to give you a quick view of some of the climate-prediction.net results. So I'll give you access to, hopefully give you access to some of this in a few minutes. But this gives you an idea of how you can look at some of these results and how they can be very different. So this is an initial condition ensemble. This is a 500 members climate-prediction.net initial condition ensemble. And it's looking at temperature and rainfall in the Mediterranean basin in summer. And what you're seeing at the top here is the distribution across that initial condition ensemble in blue for pre-industrial carbon dioxide levels, and in red in close to equilibrium doubled pre-industrial carbon dioxide levels. So 280 parts per million, 560 parts per million. So you've got two distributions there. And then below it you can see the distribution of the change in Mediterranean basin summer temperatures. So you've got very much a peak at around 5 degrees of warming there. Rainfall, the same sort of thing, but now in the Mediterranean basin in summer, the double CO2 has gone down in precipitation, and that's what you see in the distribution of changes. But here the distribution of change is much bigger. It's sort of it's from minus 20% to minus 50%-ish that we're looking at. So quite a big change there. And then you can pick out those. These are averages over the. What I was just showing you is averages over the Mediterranean basin. But if instead we can look at the different maps here. Now we've got a problem. We've got 500 members. How I could give you 500 maps. That's not going to be sort of terribly useful. So what we've picked out here is one that is on the 10th percentile of the regional temperature change. So this is a 4.9 degree warming, and the median is 5.5 degrees, and a 90th percentile would be 5.9 degrees. So here we've got 5.9 degrees regional warming, 4.9, and you sort of picked out an extreme one as well, sort of at the real high end, which in this case was 6.5 degree warming. So the point here is that different initial condition members have different degrees of regional change, even though they're fairly similar. There's only a degree different. On the other hand, in the world where we're trying to restrict global warming to 2 degrees, a degree is quite a lot. But still, within those, you can get really quite different patterns of response. And yet there are some things that stand out. The land always warms more than the oceans. So there are clear signals that you can pick out, but the details of quite where you're going to get warming might be different. Now if we go over to a perturbed physics ensemble instead, and say, okay, we're going to change the way our model represents all sorts of different processes. Now we have a distribution of temperatures. If you remember the previous one, it's very constrained. It's really quite fixed for that initial condition ensemble. Once you start playing around with how the model works, how it encapsulates different processes, you can get a range of 6 or 7 degrees in the pre-industrial temperature. And you can get an even wider range in the response to double CO2, such that these two overlap. So you could use that as an argument, maybe you shouldn't worry about climate change. The sort of these two things are overlapping. But that's not really the point at all. What you want to do is pair these up so that for each version of this model, you look at the change in temperature. And that's what we're doing at the bottom. It's the same as the previous plot, but now we're looking at the change within each particular perturbed version of the model. And it turns out that they all warm. Well, of course they would. They have to. This is an energy conservation sort of thing. But how much they warm varies quite a lot, anywhere from 2.5 to 8.5 degrees, which reflects the fact that these different versions of the model have different climate sensitivities, actually, even though we're now looking at the regional level. And a similar thing on rainfall, we get an overlapping distributions, but actually, if you look at the change, all of them show drying of the Mediterranean basin in summer, from not very much, almost zero, down to sort of minus 70%. And yes, then we have, when we look at particular maps, the 10th percentile can look quite benign here. But that's really because you have to choose a colour scheme that can go up to really high levels. So I mean, some of these are sort of maybe 3 degrees on land, maybe only 2 degrees with a regional change of sort of roughly 2 degrees. This is still pretty significant. The 90th percentile you get in places, but even though the regional change is 7 degrees, I was going to say only 7 degrees. 7 degrees, of course, is very huge. But within a 7-degree change, the land warms more than the oceans, and we're looking at places in this particular one which would be up at 11 or 12 degrees of warming. And that's the 90th percentile, there's another 10% beyond that. So the perturbed physics shows you a much wider range. So, summing up, what sort of model should we use? What's famous courses? Oh, this is sort of connecting to some of the mini lectures. There's a point of, there are all sorts of different models out there. There's all sorts of ways of encapsulating climate change information, and how you do that is really quite challenging. And I guess that's something that I'm kind of working on. When we look at these complex models, we need to be really careful about using their outputs. And I say this, I guess, from a degree of frustration, because there are lots of information providers out there. Maybe some of you will go on to work for some of them. There are people providing climate services, there are people providing climate information to insurers and to banks. In terms of what's going to happen, sometimes at postcode level, so that you can assess the risk of your flood risk to your portfolio of assets, something like that. There's a lovely report which was at least partly done by the Global Association of Risk Professionals, GAR, which looked at these different service providers. This was last year, I can't remember what it's called. Analysed these results and was able to show that under different providers, you might conclude that there's no risk of flooding at all, or there's a risk of flooding up to 10 metres in large parts of your portfolio. These are very different answers, but crucially, the users are just buying one. And they're buying it because they think that it gives them the answer. And we need to be really cautious of that. Our models can't give us probabilities, but they can be used in probabilistic analyses. How we use different, how we combine information from initial condition ensembles as opposed to perturbed physics ensembles, and what they tell us in terms of inevitable uncertainty as opposed to uncertainty that we might be able to reduce. Initial condition uncertainty is kind of unavoidable. That's just always going to be there. So physics uncertainty comes down to how much do we understand about the climate system, and that's something that we might be able to develop in the future. Okay, so two things now. First are questions, and the second is I'm going to ask you to get into groups like last week and talk about the numbers that you're getting from the assignment 2.1 about uncertainty estimates. I want you to be confident that you can get the uncertainties from those data sets. And then I'd like a little bit of feedback on that, and then I'm going to give you access to the climateprediction.net data, and I'd like you to think about how that compares to the IPCC data. But first, do we have any questions from this afternoon at all so far? Apart from, I've been talking too much, but there we go. It's what I do. Okay, well, do capture me either towards the end or in the future. You can email me if you want to do that. Okay, so so you've got your assignment 2.1. You're looking at, I can't remember, I think it was Barcelona and Oslo getting numbers from the fifth assessment for Atlas. Can you just turn around and form your groups like we did last week and look at the numbers you've got? Are you getting the same numbers? Try and be confident that that you understand where those numbers are coming from and that you are kind of getting the same sort of numbers. I'll give you 5 minutes for that and then send you to
Did you guys do your awesome?
So we did half of our IR department. I'm so sorry. We did it last time. If you guys have
She was kind of leaving her technical battery.
I found it very tedious.
That little line, it's gonna be like your no,
I'm like, which one of us can use everything? You guys
that's super rich.
Yeah. We were looking at that. It's like we were looking at upper bound, and then in the middle of the. And then which the like little dash. I got 4. And then
and then I checked.
drawing lines. And that was like attached me last week. I pressed it Wrong department.
I haven't read a map.
No, it's not 5.5. I can tell you that. It's probably
forget a whole bunch
Just so different.
Oh, that's the question that I had. How do you average?
I'm doing the spatial.
like 6 hours.
But I can't.
Just the lecture and then seminars like Monday, Wednesday, and everything else. Today we had
It's getting pretty hot.
I wouldn't be able to make it for like that exact
I think it's gonna be something.
Great day.
Okay. Are you? How are you getting on? Are you all sort of happy with playing with that data set?
Just a quick question that we were debating, but when you are looking at the color in the maps and matching it up to the scale, what is best practice? Is it choosing like the median, like because the scale is, the color is between two numbers, do you put the range, do you put the average, do you put the upper limit, or no one?
So I would put the central value across those, would what I would do. But I do feel a little bit bad about these exercises. The part of the point of these exercises is that there isn't really a standard there. Part of the point is that the numbers are already vague, and kind of what I would like you to take away from this afternoon is, and I have no idea how long it will last with you or how long it's lasts with other cohorts. Because when you go out there, you will find lots of people, there'll be lots of papers giving you a number. It'll be 3.1. And kind of what I want you to have a feel for, that's likely to be pretty unreasonable. You're going to need to think about it beyond that. Yep.
A question somewhat related to that. With the drafters of the IPCC report, was there Was this like a decision for the data visualization to intentionally be rather vague and imprecise, or is that just the data being realized?
No, that's just the data being realised and needing to go into report in that case. The last couple of years I've tried to work out, should I do this with the sixth assessment report? Because the sixth assessment report produces an atlas as well, but they don't. But it's not an annex. It's only it's a web interface, and it goes into much more detail. Which kind of makes it worse. So I mean, a lot of this sort of feeds out of experience that I had more like 15 years ago when speaking to people in the development community in East Africa, where they were saying, well, you know, we're putting together our plans. What we do is we download the IPCC PDF, and he didn't have an atlas there, and he just had a chapter on different regions of the world, and we just enlarge it till we find Addis Ababa, and we read off what the number is. That's what we'll adapt to. That was a problem, and it's a problem now with AR6. But you get so much detail, but little guidance on how you should use it. Which is understandable. I mean, I'm not giving you very much guidance, am I? Because there are a lot of difficulties here. Okay, so that was all from the CM5 ensemble. So just in terms of playing around with these data sets and thinking about these data sets, you can access the prediction.net data, or some of that, by going to this web page. You'll no doubt have it on your screens anyway. Username, distributions, password ESS2016. Let me just show you what that looks like, if I can. So that will, once you've logged in, it'll take you to a screen like this. So then you can choose your region. So maybe if I think about what we've been looking at the Mediterranean Basin, so you can choose the Mediterranean Basin. And you can then choose your season, so to align with what you're doing, maybe look at the June, July, August. And then you can choose whether you want to look at an initial condition ensemble or a perturbed physics ensemble. I don't know, I imagine you will, it's never quite clear to me what things have been picked up, but just to emphasise the point, the initial condition ensemble has to be based on a particular version of the model. So the initial condition ensemble is based on the original unperturbed version of the model. So we have, it's taking that unperturbed version of the model, the standard version, and just changing the initial conditions. The perturbed physics one, many versions, is taking that original model and then changing the parameters within that model to get lots of different versions of the model. It would, of course, be possible to take that original version, change some of the parameters, and then run a new initial condition ensemble. And indeed, that's what one should do. But even we will limit it on our computing resources. In fact, we did do that when we were only able to run 5 to 10 members, whereas we ran a larger one for the initial condition ensemble based on the standard setup. So if you then go to this is exactly what I showed on the slides, isn't it? So I should have gone somewhere else. Okay, let's choose a different region. Choose Northern Europe, and let's choose winter, and we'll take the initial condition ensemble. So that gives you exactly the sort of thing I was showing before, these different distributions, but it then allows you to pick out the range of regional temperature change, there is also the global information there. So you're getting a range of 4 to 8 degrees for, this is the initial condition ensemble, is it? Yes. And an increase in precipitation of between 10 and 50%. So you've got that sort of data, which I think is what I would be, am I looking at that? Yes, I am. So that's, so in terms of what I was asking you to do of gathering these data into those boxes, if you think about Northern Europe, this has to be, this is the equivalent of the regional average for that Oslo section, and you'd want to compare that 4 to 8 number with, I don't know, what did you get? What did you get for winter regional average temperature change from the IPCC Atlas? Okay, so I think I was looking at a sort of central value of about 3.5 and a range of about 1 to 6.5. So it's sort of very much skewed to over here. So it's a different ensemble. It's a different ensemble. It's also, but it's giving you a different range. So here we have already a wide range. You can get a different range from a different ensemble. Yeah, what do you do with that? Okay, so what I would like you to do is go away and look at the climate-prediction.net results, gather some of the data alongside what you already have from the IPCC Atlas. Spend sort of 2 or 3 minutes just gathering some of that data. You can have a play around with this data. So this isn't a fixed thing. You can choose a different place in the world if that's of interest to you, or you can fill in these boxes for Oslo. As your group, maybe just choose somewhere that you would like to think about, and look at what data you can get from the IPCC Atlas. Look at what data you can get from the climate-prediction.net, and think about how they're similar, how they're different, why are they different. Maybe talk about why they're different, what sort of adaptation activities you might foresee in those sort of regions. Think about sort of what sort of thing that region might need to adapt to, and to what extent do these numbers support and help you with that, and to what extent are you left running away screaming that I just don't have the information that I need. That's pretty much what the other thing I was going to say. So, so I'll give you sort of 15 minutes to play around with that. Do come and find me if you want to ask questions or raise things, but then we'll give you sort of 5 minutes to respond as a group. Okay?
I think I'm getting this lecture is
No, I was just thinking, if the climate kept doing this, they would be like me. It's good to know that like water is I know. Not doing it, still gotta try, and then be like, okay.
Other thing that he was saying about
This would be fun. We have like 3 hours, 7 hours for all of them. Yeah, I'm from the IR.
That's the first one.
the same thing that was said with the dice.
That's how big it is.
No, that is literally. Oh wait, no.
This is all deterministic. We have no free will.
Especially for the one. That's weird. Okay, so
I see what you mean.
but the one thing.
That's the lower end.
That's the takeaway. This one actually part of studying and not having a
You're trying to dump to something. It's exactly this. You should
I'm in.
Always supposed to do it.
She's American.
Like 7 fish. I'm counting real days. Counting my days till I get hurt. It's gonna get better. It's gonna get better.
Ways. I mean, not bad. Policy in the time. It's like very
Abandoned all of them.
Okay, never had it.
So that would have been the fish.
taking these big things value. We're in the bedroom. God forbid we do.
You're like, they know it.
I worked for years as an ESG consultant in startup. And I went to buy it's like my prospect. It's my like I know if I was to make yeah. Wait, I was like I wanted to get like
Basically, you're saying this one, buy.
yeah.
These are all pressure.
Oh, it's just like this.
to say regarding it's pretty gaming. It's on my list. Oh yeah, you have to have your okay, you in New York you need to have your dog that way.
Sure.
Taking your dog. On this, it's just like the phrasing. What did I say? I forgot to name
You can
they're in the bag.
the IPCC doing 6 months? I thought they were just doing it. Oh yeah. Yeah, no, that's right. Yeah. So that's the only comparison you can make.
That doesn't seem
Yeah.
Or just stick with winter Easter side, because that's like.
I would stick with winter and summer, but yeah. I know. But it's a really important point. But this is also the way of the data set.
When I get home, though, we'll probably
So much despair in his eyes.
I'm like, you are all
Too young.
you can probably get any of us to take together. Yeah. I know.
Hello.
The first question is, for what there are those predictions?
So these are just these maps are just so for
wait to see what we're gonna get. Oh my god, stop.
reasonable. So these are just samples. So this is a the 10th percentile of the regional temperature change. So if you average over the whole of the Mediterranean basin, this is one. And you can physics of okay, so you're looking at a particular simulation that has a 5.2 and then you're looking at a particular simulation that has a 5.6 degree warming on it. And there you're looking at a particular simulation that has 5.9 degrees.
Where's my time?
It's on the border. And you can pick out that big. That's how it varies with the overall regional change. But that's just one sample. But then the question is, how would you use it? Yeah. So I mean, and you can come back to that. This is just an exercise to play around with data. Realize
He's like never gonna let us know what he again.
Provide what you need. If I had longer or had a whole afternoon on this, I would focus on particular decisions, say around Barcelona, and think about listing what you would want, what other data do you want to see all 500 of these? Or would that be useful to think about what's going to be useful in making your decision? What decision was it you chose? What factors are the factors that impact that, whether it's standard factors or non-standard? So this is kind of where I'm going. It's really just a be aware of the challenges in the data. Yeah? That's a very good question. So, I largely these exercises sort of imagine that there's equilibrium. So one has come to so it's not because but do raise it. We won't have long to discuss. So these are important points.
Okay, now understand. There's something you're not go down. What question do you
So bad. Like I didn't really like I need to push myself. I don't believe in nature.
Destroy it. Patient. So you just, let's see, you just lose this.
I think I texted they made me like right? They're still like not realize that's how I call my schedule. My walking home. September, I was like, damn, I would have had one.
He's like more very perceptive.
So much better.
Very experienced. Yeah, but not for like long time. Family?
Okay. So, just ask questions or provide feedback on thinking around these data sets. Already, some people came up asking some good questions. Anybody want to raise issues? You're a strange bunch. You're so good at talking with each other. Sometimes people just you can't get groups to work at all, and you're brilliant at it. But but a bit silent now. Yeah.
Okay, like we were discussing how there are so many different climate models and climate scenarios that sometimes it becomes very difficult just to connect to policy what we should take. Like sometimes it could feel like a very cherry picking to take like one model or another. However, I think that like having this literacy about the different models would help us to understand the science behind it to make better policy decisions for the future.
Yeah, I think that's a really good thing. But I mean, I've been in this sort of business for 25 years, and it's, in some ways, I'm only just beginning to get how little guidance there is out there on how to process the different types of information. And of course, this afternoon is just meant to give you an idea of playing with it. So it's not answering that problem, but there's a real need for that. Anyone else? Yeah.
I was just wondering, with the graphs talking about the change in the temperature, the bottom, the x-axis I got, the y-axis, what is that in reference
What's the
to?
y-axis?
Yes.
Yeah, fair enough. So it's always a problem, the y-axis. It's probability. Yeah, so it's probability, and it should kind of be labelled as probability. But once you start labelling it as probability, you've got to say, well, okay, what are the units of probability? And that then sort of gets complicated. It's kind of number of simulations, whether that's initial condition simulations or perturbed physics simulations, that are found within a half-degree range or something. Or actually, it's a fraction of the total number of simulations that are found within that particular range. So if you start putting numbers on that, they get really quite weird. But if you just look at it as probability and think about it as probability, it's quite easy to understand. Where it's higher, there's a greater probability. Yes.
Thank you.
Anyone else? Okay, so the idea of this was to give you some time to play around with the challenges of the sort of data sets you might come across. One of the things here is, so climateprediction.net is absolutely great because it's the largest exploration of model uncertainty anywhere in the world. It's 20 years old and it's still the biggest exploration. So it's great. It gives you that idea of model uncertainty, which you won't get anywhere else. And it's much bigger than any of the CMIP ensembles, which is great. On the other hand, it's an idealized scenario, which is double CO2. And we only have a certain amount of data that you can get back from the simulations. So you only have regional averages for most sort of things, which is not much use in many ways. And besides, it's a fairly old model. So should you take CMIP6 instead? Well, you could take CMIP6 because that's the latest model. The latest model ensemble. On the other hand, we know how constrained it is, and it's climateprediction.net that tells you something about how constrained it is. And so there isn't an answer, and many people in business and industry are very much looking for an answer. They don't want to be interested in these questions. They want to have the data that they can feed into their risk management processes. And that could be risk management for portfolio, of a business decision, or it might be of a flood defence system. You're building flood defence. Tell me how high it needs to be. Just tell me how high. Just tell me the amount of rainfall. And the friction we have here and the challenges we have in mitigation and adaptation is that there is no simple answer to that. It's going to be different every time. Yeah.
I have a question regarding the inherent plausibility of some of those models, because I've read before that I think it's RCP or SSP 8.5, that there's some inherent plausibility questions there, because I think to reach that we would need to burn more coal than we could like financially burn, or like would make sense financially to burn, and that sort of then is a bit impossible.
Yep.
What's your stance on that?
Okay, good question. I have a number of views of that. There have been major criticisms by some people that the 8.5 runs are run at all for this reason, that they're not credible. An initial response to that would be it's driven partly by scientists, and the scientists are wanting to get a signal. They're wanting to understand a process. And if you hit the system harder, you're more likely to get a signal. So actually, I think there's still value in these high emission scenarios because you will learn about the system. Okay, but that's very much a scientist response. So as a sort of social scientist, and there is a problem there that both the scientists and activists will tend to choose that high emission scenario because it sounds more dramatic. And there's a problem there, yeah. I do accept the criticism that they are misused in that sense. But I would give a final thing here. So a lot of those criticisms started sort of 2 years ago, or a little bit longer, when I think the general view of the world was we accepted that climate change was happening. How quickly we respond might still be open to question. Whether we achieve Paris 2 degrees will be open to question. But we were all going along that line. And the world looks very different now, both in the US but also here and in Europe. But it's not clear where we're going to be in another 2 years' time. And so practical stuff that I didn't know. I wasn't aware that 8.5 was a matter of we couldn't burn that. I thought it was a matter of policy scenarios meant that you thought we just weren't going to go there. And I think a little bit of me at the 10% level goes, actually, looking at the world now, it might people choose to go there. So I'm not sure it's so unrealistic. But still, basically I accept your point, yeah.
And follow-up question. I've heard that also some of the tipping points, or many of the tipping points, are not modeled into the systems, like for instance, like the methane in the permafrost. Yeah. So can you actually argue, okay, well, this is not modeled in, but we still want to see the edge cases, and then therefore this makes sense?
Very much. I think that's a very good argument for the high emission. But it's still, your question still harks to the communication problem. If you're an activist and you pick out that scenario, you kind of need to associate it with, I'm including this because I'm interested in the risks of crack rates and methane hydrate release from permafrost or from the oceans, which could lead us there. And if you don't say that, then you run the risk of people coming along saying, but hold on, that's not a credible scenario. So, yeah, the communication becomes difficult. So I'm going to leave you, because I need to leave you very soon. I'm going to leave you with a very quick summary of the sort of 7 characteristics of climate change, which form the first chapters of my book, which I think are available from the library too, just these first chapters, but just sort of highlight how I see climate change. Firstly, I think it is all about prediction. So I do a lot of stuff on adaptation, so that's important, but I think it's also important for mitigation. I think we have some idea of what the world will look like in 2100 if we achieve global net zero in 2050, and we have some idea of what it would look like if we don't achieve global net zero in 2100 or don't do anything at all. And I think we have, each of us in our minds, some idea of what that world might look like. So when we're deciding to tackle climate change, that comes from, I prefer that world to that world. And the more we can say, and the more reliably we can say something about what those two different worlds are, the better information we have for making social decisions about how much, why it's worth tackling, how much it's worth tackling, how we deciding about investment on climate change as opposed to investment on education or health or food or whatever it might be. So I do think it's all about climate prediction, but it is an extrapolatory prediction. It's taking the system beyond anything we've seen before, which means that the information isn't necessarily in the data set, and that's a huge problem. It's also it's also a prediction, extrapolatory prediction of a complex non-linear system. So you get these sensitivities to initial conditions, which means that the best sort of prediction you can imagine, even if we had a perfect model, would be a changing probability distribution going forward. It's not a simple, this is what's going to happen. It's some sort of distribution that changes over time. I have lots of illustrations of that in my book, actually. When one sort of idea of that is here, although it's not for a climate model, it's for a simple non-linear dynamical system, but you have this changing distribution over time. That's what climate change is. It's a changing distribution of time. That's what climate prediction is. It's a change in distribution over time. Reality will only be one sample from that. So it's like a single trajectory here. And so, you know, in this particular idealized world, you're getting a change in some value. You now are in a world where there's quite a wide distribution here, but you don't explore parts of it for another 50 odd years or something. Our sample, what actually happens is just a single trajectory, which means it's a one-shot bet. There are uncertainties in what will happen, which we might be able to reduce because of understanding, but the uncertainties we can't reduce, and so you might just get lucky or you might get unlucky. And that's an element of the problem. It's a risk element of the problem, but we only get to play it once. You only get to play the game once, which means raises all sorts of questions of your attitude to risk and society's attitude to risk. And most people's attitude to risk, and most of insurers' attitude to risk, is based on the idea that you get to play the game multiple times. You take out insurance multiple times, or you get to play poker multiple times. You don't aim to win on every occasion. You aim to win on average overall. But that's not the character of the climate change problem. You only get to play it once. So what gamble are you willing to take? This is also in a world of growing computational capacity, so computers suck in most of the research. It provides all sorts of opportunities, but it also distracts us from understanding the system as well as we might like to. It's also a fundamentally multidisciplinary problem. You guys perhaps know more than many others. Yeah, you're in this class and you're faced with me, and I do feel sorry for you about that, but you're faced with me in these first 2 weeks in the physical science world, but most of you are social scientists. Even within the physical sciences, there are all sorts of different disciplines that come together. You've got the chemistry, you've got the physics, you've got the maths, the geomorphology, the statistics. All these different worlds don't talk to each other very well. And then on top of that, you've got all the social sciences. You've got psychology and sociology, the human geography, policy development, adaptation planning, not to mention economics. And all these interact with each other. How you do one depends on an understanding of another. And we're not good at talking to each other. In fact, we're really bad at talking to each other, and information doesn't cross well between these disciplines. This is a really huge barrier to us acting effectively on climate change. And I'm not sure this is a good example of it, but it's still one that I like. This is a sign in Wales, just meant to illustrate the difficulty of sometimes getting the information you want. At the top it says, no entry for heavy goods vehicles, residential site. only, which is a fairly common sign. In the UK, underneath it says in Welsh, I'm away from my office at the moment, please send anything you want translated. And so some guy sent a message to the translation department saying, I'm making a sign, I need to translate into this. He went away for lunch, he came back after lunch, and there was this message there, which is on the sign. I would argue that we are in a similar situation with some of these disciplines in climate change. But all of this is within the context of urgency. So this is my last point, and this is something you know, I expect. But there's a crucial thing here in economics, but even more so in science. Things go along at their own pace. We get things wrong. We sort of put science up on a pedestal, this great means of understanding. And to some extent it is. But the latest science, the latest research science isn't. It can get things wrong for decades, for centuries even. The whole theory of how things work in different areas, I've got a couple of examples of these.